So since all I need to make a resistor is just some length of wire, and it's actually one of the better labs that we have where you do have a length of wire and you measure the resistance, and from that you actually figure out what resistivity is. Actually, in one case, you figure out what the resistivity is, and from that you figure out what the material is. In the second case, you know the material is copper, and you sort of try to see how close you get. So I can treat this as one really long piece of wire or as two smaller pieces of wire. So I'm doing it both ways. So here's the long piece of wire. Or treat it as two pieces of wire. The resistance of this right here is just rho L1 over A. And the resistance of this piece right here is rho L2 over the A, which is just this right here. This is rho L1 over A plus rho L2 over A. In essence, what I'm showing here is that the equivalent resistance for resistors in series is just R1 plus R2 plus however many resistors I have. A slightly different tact here. If I have a resistor R1 and then another resistor R2 hooked up to some battery, I now have current flowing through it. Because there's no junctions anywhere involved here, this is a series circuit. So no junction, series circuit. And so when you're trying to find equivalent resistance, the question is, if I wanted to just replace this with a single resistor, what would that be? Well, I have a certain amount of current flowing out of the wire here. This has some change in potential of V, I'll put a little PS there for power supply. Whatever it gains going across the battery, it has to lose going across the resistor, because I have to end up at zero. And so I have the change of the voltage across the power supply minus the change of the voltage across the resistor is equal to 0. And I know that the change of the voltage across the resistor is equal to I times the equivalent resistance. This is Ohm's law. And this has to be equal to what we have up here. So I gain some potential going across the power supply. I'm going to lose some going across the resistor 1. I'm going to lose the rest of it going across resistor 2. So in other words, my change in the potential across my power supply minus the change in potential across resistor 1 minus the change in potential across resistor 2 is equal to 0. So the change in voltage across the power supply is equal to delta VR1 plus delta VR2.
Wouldn't it be negative?
I put the negative sign in here because I know it's going to be a loss. If I could have put a plus there, and then these will be negative numbers. It depends on where you want to stick the minus sign.
Okay, I see.
With resistors, this is the way I tend to do it. And so this would be I times R1 plus I times R2, which equals I times R equivalent. And so if I equate these two right here, I got I in common, I can divide it out, and I'm left with that. So just a different way of doing the exact same thing. Questions? let's do parallel. So I got the power supply here, resistor 1. Resistor 2. So I have some change in potential going across the power supply, as before. Now it doesn't matter which path I take, I should still end up at 0 when I get back to where I started. So I gain going across the power supply, I lose going across R1, I end up back here. This is going to produce some current coming out of the power supply, which I'm just going to call I. That is going to split. I have current I1 going across resistor 1, current I2 going across resistor 2. This is the junction rule, or the current rule, Kirchhoff's junction rule or current rule, that whatever current flowing in has to be the current flowing out. So I know that the total current is equal to I1 plus I2. Using Ohm's law down there, this would be delta V equivalent over the equivalent resistance is equal to delta V1 over resistance 1 plus delta V2 over resistance 2. Well, the voltages are all the same. If I'm going from here to here, I got 3 different paths to take, and I'm going to get some loss in potential any way I'm going. If I'm going from the right to left. So all my delta V's are the same, and so I get 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. And so this is parallel. The opposite of the rules for capacitance.
Dr. Fox?
Yes.
You said there were 3 paths to take, but I only see 2.
1, 2, 3. I could go across the battery the back way.
Okay.
Is that sufficient?
Yeah.
Okay. All right, so let's do some numbers. And then hit you with a philosophical question, or a conceptual question more. Three ohms, 4 ohms, 12-volt power supply or 12-volt battery. So in multiple questions, at some point you'll hopefully get comfortable enough where I can just jump straight to what's the current flowing out of the battery. But for right now, we'll start out with the first question of what's the equivalent resistance?
7 ohms.
So that's my REQ. And now, what's the current flowing out of the battery?
Volts?
No, not
sorry.
12 volts.
Isn't I equal to, is it charge times voltage?
Use Ohm's law.
Use Ohm's law.
That delta V over R.
Yep. Since the potential, it's a simple circuit of just a single resistor, whatever, I gain 12 volts here, so I gain 12 volts going in this direction, I lose 12 volts going in that direction. But the potential, change in potential across the 7 ohm resistor, ignoring sign, is 12 volts. No, delta V equals IR. So that's 12 is equal to I, so 12 volts, I times 7 ohms. So 12 volts over 7 ohms is equal to I. And I realize we've done stuff with current, but never actually talked about the units, so let's talk about units here. So the math problem is 12 divided by 7. And then, yes, volts per ohm is not wrong, but we can do better because that's too much for physicists. Anyone know what the standard is?
Amps? I said amps?
Yep. Amperes, or amps for short.
Can we write just amps?
Yeah, or just the letter A,
Okay.
capital
A capital A.
I guess it's. So that would also be a coulomb per second. So I guess technically that's the one that's by definition. Because it was charge divided by time. And for purposes of the camera, so ampere by definition is a coulomb per second. Think change in Q over change in time. But that's also equal to a volt per ohm. And think of delta V over R. Now, a pet peeve of mine. The term amperage. I do not accept that as a real word. I know that I've had enough people in my classes who have worked with electricians and have worked in various fields within the stuff related to this, where it is a common word that is used, but I do not accept it. The word is current. It's fewer syllables, fewer letters. Save ink, use the word current. And I will fight that till I die, and then I won't care.
Wait, so if we find this like 12V over 7 ohms, should we give the answer with the unit I?
No, the unit would be A.
Right, but just call it current?
Yeah, so the current is 12/7 amps, or amperes.
Oh, okay.
Yeah.
The,
I'm not objecting to the use of the word amp or ampere, I'm just objecting to the word of amperage in place of the word current.
okay. Oh, okay, I see.
So over here, this is not an acceptable way of writing the answer right here. This is an acceptable way, or 12/7 amperes.
Just to clarify, the ohm symbol, is it a straight line and then a little lump and then another straight line, or is it?
Wait, sorry.
I'm sorry,
It's like a
ohm?
little horseshoe.
Oh, negative.
Yeah, it's like.
Oh, it's-
Yeah,
It's a capital omega.
okay,
That looks closer to that. Those are supposed to be level.
okay, good to know, thank you.
The lowercase omega we've used before for angular velocity and angular frequency. That's the lowercase,
Mm-hmm.
the uppercase.
Gotcha, thank you.
Yeah. I got my battery here. Oh, and by the way, the battery or the DC power supply has two unequal length lines. Capacitor, the lines are equal length. Now, I might get sloppy when I'm writing up here, but the intent is capacitor, DC power supply. There was at least one thing I saw recently where this was being used for capacitor, and that's not appropriate. All right, so DC power supply hooked to a, oh, why not, 3 ohm resistor and a 4 ohm resistor. So, we'll just start out with equivalent resistance.
It's just 1/4 plus 1/3, right?
Wait, say it again?
It's 1/4 plus 1/3.
And then take the reciprocal once you've added those.
Right. That's, I got 1.7.
Me too.
1/4.
It's 12/7 again.
Hmm?
It's the same, it's 12/7 again.
Ah,
5, 6,
same point.
something like that. Right, so, or in fraction form, 12/7. Units? More than just a mantra. All right. So here's the conceptual question. If I started out with this circuit with just the 3 ohm resistor, why does adding a resistor drop my resistance? How does that make any sense that, so I start out with just that, I add a 4 ohm resistor and I drop my resistance? Yes?
Does that have anything to do with the junction? Like now the current has like 2 options of where to go? Like it splits the current, so.
Yes.
That's what
Ultimately it does.
Is that the reasoning?
And I'll take it one step further.
Okay.
It does, the junction is very key there. But recognize when I start out with just the 1 resistor here, current's gonna get to, if you consider this a junction, it's got this path right here with some resistance, or this path this way which has infinite resistance. So, yes, we are adding a resistor, but we are reducing the resistance of that path from infinity down to something not. From another point of view, think of resistance as, well, resistance. That was insightful. If you can picture the lab room, I like the lab room better for this, but we'll do it here. We'll do make-believe. There's a fire in the room, and we're gonna all try to get out the door. There's a limit to how many people we can get out the door at one time. But if suddenly another door appeared back there, no matter how big it was, I mean, it could be a very small, slender thing so that only maybe 2 of us could get through it. Well, at least that's 2 more that aren't gonna be jamming this up. And we can get everybody out of here faster if there's another way out. So the same here, most of the current's gonna go this way, but not all of it. This is enough for some to go through it, and therefore we reduce the overall resistance.
Does most of the current go through the 3 ohm resistor because it's a lower resistance? It has nothing to do with how you've drawn it being closer to the battery?
Correct. Yeah, if I switch the 3 and the 4, it still mostly go through the 3.
I see.
Now let's apply Ohm's law and figure out how much current's coming out of the battery in this situation. I know that I have current coming out of the battery and it's going to get to the junction. From there, it's going to split. So I'm going to just call this I sub 4 and call this I sub 3. I'm going to apply Ohm's law here. So I'm going to start at this point right here. I'm going to go across my battery and I gain, so let's just make this a 12 volt battery. So I have 12 volts going across here. I come up to here and now I'm going down this other path, the middle path, the way I've drawn it. And my voltage, the change in potential is, well, 3 ohms times whatever I3 is. And then I get back to where I started. So it should be at 0. Doing the fancy math, I3 is equal to 4 amperes. Let's take the other path. I start here, I go around, I gain 12 volts going across my battery. I now go this path up here where my current's I4. I'm going across the 4 ohm resistor. I know my loss is going to be 4 times I4. And then I get back to 0. So I4 is 3 amperes. What is the current coming out of the battery?
Amperes? Is it 7 amperes?
It is indeed. Because at the junction, coming out of the junction, I've got 4 amperes and 3 amperes. Therefore, coming into it, I have to have the same amount. So 7 in, 7 out. So I've got some sort of power supply here.
Does that notation mean something different with the circle?
A little bit. From a physics point of view, no. From a real life point of view, yeah. You still have the squiggle in there. It's a resistor. That, in essence, is the heart of it. When you put the circle around it, typically you're meaning it's a light bulb. Incandescent light bulb, the classic. You run current through it, it heats up, it glows. Incredibly inefficient, so there are fewer and fewer of those around. But still,